Imagine asking a contractor for, a simple wooden birdhouse, right?
Right.
You step away for a cup of coffee.
Right.
You come back 30 minutes later, and they've somehow built a 3-story mansion on your front lawn.
Oh, man.
But all the doors open upside down, the plumbing routes straight through the chimney, and the foundation is literally made of cheese.
Yeah, that sounds about right.
That is exactly what it feels like to delegate complex coding tasks to an AI right now.
So, welcome to today's deep dive. It is Sunday, May 31st, 2026, and we are tackling a very, very modern frustration.
We really are.
We all want the machine to do the heavy lifting, obviously, but somehow, trying to manage an autonomous coding agent, it often creates significantly more work than if you just, wrote the boilerplate yourself.
It is entirely the defining bottleneck of software development right now. I mean, we have these incredibly capable large language models, but our operational relationship with them is fundamentally broken.
We're basically trying to manage supercomputers using the exact same oversight strategies you might use for, like, a hyperactive intern.
A very caffeinated intern.
Exactly. So today we're looking at why our current architecture of human-AI collaboration is failing, and how a concept borrowed from systems engineering offers this highly practical way out.
And to guide us through this, we have a genuinely fascinating blog post by software engineer Lucas F. Costa. It's titled, "Backpressure is All You Need."
It's a great read.
It really is. The mission for this deep dive is to figure out how to successfully delegate to AI without micromanaging it into oblivion and, without letting it deploy total chaos into your production environment.
Right.
Okay, let's unpack this. Because before we can look at Costa's solution, we kind of have to look at the wreckage of our current workflow.
Yeah, the wreckage is a good word for it.
Costa argues there are basically 2 default ways developers are using AI right now, and both just create these massive bottlenecks.
That is the core of the problem here. When developers get their hands on an agent, the first instinct is to just let the LLM run completely unattended.
Oh, totally.
You give it a massive prompt, maybe an entire feature request, and you just step back. The assumption is that because the model can generate tokens incredibly fast, sheer velocity is just going to solve the problem.
I will admit the temptation to do that is huge.
Yeah.
But I actually want to push back on why this is considered a failure.
Okay, sure.
Because, if the AI is so incredibly fast, why not just let it run wild and fix the bugs later? Isn't speed the whole point here?
Well, yeah.
It's like having an overeager developer who can write 10,000 lines of code overnight.
Yeah.
Sure, they might break the staging environment, but the sheer volume of output means you're getting feature work done faster.
You're getting code generated faster, sure. But code generation is not the same thing as shipping a reliable product.
Okay, fair.
Speed without boundaries is actually totally destructive to a code base. Costa observes that when you let an AI run unattended, you don't just get bugs. You get deeply confused architectural changes, hallucinated dependencies, just, massive pull requests. And because the AI generates the stuff so fast, the human reviewer simply cannot keep up with the volume of the diffs.
Oh, so you just get overwhelmed.
Exactly. The sheer scale of the PR forces the human to lower their standard of review. You end up blindly merging code that you don't really understand, honestly, just to clear your queue. The velocity of the AI forces the human to become a bottleneck who basically just gives up.
Wow, so you've essentially forfeit code quality because you just don't have the cognitive bandwidth to audit like 5,000 lines of AI-generated spaghetti.
Exactly.
So if abandoning the wheel leads to a degraded code base,
Yeah.
the natural human reflex is to grab the wheel tighter. Which I guess brings us to the second approach, right?
Yeah.
Reviewing every single line as the AI types it.
Yes.
Treating the AI like a glorified autocomplete.
And that creates a completely different bottleneck. If you force a human to sit there and review every single tiny step, prompting the AI, waiting for the output, checking the syntax, finding an error, explaining the error back to the AI, you haven't actually delegated anything.
Right. You're just babysitting.
You are just typing with a highly unpredictable, very verbose keyboard.
Think about your own workflow yesterday, right?
Yeah.
How many times did you run a build, get some massive Vercel deployment error, highlight it, copy it, paste it back into Claude's chat window, and hit enter?
Way too many times.
Costa has a devastatingly accurate phrase for this. He says we have ironically promoted ourselves to an expensive clipboard.
It hurts because it's true.
It really does. We're highly paid professionals doing the mindless mechanical work of passing error logs between two machines.
It is a profound waste of human intellect. We're acting as the manual glue between the runtime environment and the language model to automate this pushback to basically stop being the clipboard. Costa argues we need to import a specific concept from systems engineering, and that concept is backpressure.
Okay, let's define the mechanics of backpressure. In the past, I've heard this described using, like, restaurant analogies.
Okay, let's hear it.
It's like a restaurant kitchen. If the waitstaff keeps punching in 100 orders a minute, but the chefs can only cook 10, the whole system just collapses. Unless, of course, the kitchen yells, "Stop taking orders."
That is actually a perfect way to look at it. It's a mechanism where a downstream consumer automatically forces the upstream producer to slow down, buffer, or just shed load.
And without that kitchen yelling to stop, the waitstaff just keep taking orders at maximum speed, totally oblivious to the downstream disaster in the back of the house.
Exactly. What's fascinating here is that software engineers actually know this lesson intimately.
We do.
Oh, yeah. We rely on backpressure constantly in traditional development. We just kind of completely forgot to apply it when LLMs showed up.
Wait, how so? Give me an example.
Well, look at the history of web development. Writing plain JavaScript 10 years ago had zero backpressure.
Oh, God. Yeah.
Right. You could pass a totally malformed object to a function, and the editor wouldn't say a single word. The producer, you, the developer, could just keep typing.
Yep, completely blissfully unaware.
Exactly. You wouldn't find out you made a mistake until the code was actually deployed, a user clicked a button, and the browser's through a, props.onSubmit is not a function error. The feedback loop was massive, and the human had to manually trace the bug.
And then TypeScript came along.
Yes.
And it fundamentally changed the workflow by adding immediate backpressure. It made impossible states impossible at the compiler level.
Precisely.
If a component expects a Boolean and you try to pass an array, the editor just throws a red squiggly line immediately. It refuses the work at the boundary. The machine physically stops the developer from moving forward until the types align.
And automated tests and CI pipelines do the exact same thing at the repository level.
Why? Right.
You cannot merge your branch if the linting fails or the unit tests don't pass. The pipeline pushes back autonomously. We spent decades building automated guardrails to take the manual no off the shoulders of human reviewers.
Yeah, that makes sense.
But when LLMs arrived, because they interact through these conversational chat interfaces, we threw all that wisdom out the window. We went right back to making the human the default backpressure.
Okay, so the architectural challenge is clear. We need the AI to manage its own messes.
Yes.
We need to design an iteration loop where the AI hits a wall, reads the error, and corrects itself without a human ever looking at the screen.
That's the dream.
Costa initially experimented with Claude's built-in goal command to achieve this, right? But he found it didn't really work out of the box.
Yeah, the intention behind the goal command is sound. I mean, you give the model a target, and it operates autonomously until the goal is met.
Right.
But mechanically, Costa found that the AI would constantly declare victory way too early.
Oh, interesting.
It would build the happy path of a feature, totally ignore the edge cases, write zero tests, and confidently announce that the job was finished.
Wait, I have a probing question here.
Sure.
Claude has been trained on millions of repositories. It knows what a robust test suite looks like. Why do we need to build a convoluted external loop just to force an LM to do something it already knows how to do?
Well, because knowing the syntax of a unit test and maintaining the executive function to write one after generating a massive block of code, those are two very different things.
Oh, I see.
It really comes down to context window degradation. As the AI generates more tokens, its attention mechanism gets diluted.
It gets distracted.
Exactly. It gets hyper-focused on the immediate task of getting the feature to render, and the broader system prompt requirements like, always write comprehensive tests, they just fade into the background. Without enforced automated boundaries at every single step, the model just loses the plot.
So Costa's fix was to build a really rigorous loop. He basically forced the AI to run linting, testing, and simple verification scripts, not just at the end of the prompt, but inside every single iteration.
Yep.
If the AI writes a function, the loop immediately runs a test. If the test fails, the loop captures the error output, feeds it back into the model's context, and demands a fix.
It forces it to deal with reality.
Right. The AI keeps bumping against the guardrails until it learns the shape of the road. But there is one specific addition to this loop that I found is totally revolutionary. Costa added an entirely new phase right up front before a single line of actual code is even generated.
The planning phase
Yeah,
review.
the planning phase.
This phase addresses the most expensive mistakes you can make with an agent. I mean, an AI cannot course correct its way out of a fundamentally flawed architecture.
Oh, definitely not.
If it decides to use a totally inappropriate database schema, running a million automated tests later on isn't going to save the project. So Costa configured the system so that before execution even begins, Claude has to formulate a plan. Then, the system spawns a separate reviewer subagent to critique that plan.
Wait, I have to challenge the logic here.
Go for it.
If an AI is prone to hallucination and poor architectural choices, isn't having it review its own work just creating an automated feedback loop of bad decisions? Like, how do we know this subagent isn't just rubber stamping the main agent's mistakes? Because they basically share the same underlying model weights.
It's a critical question. And the reason it doesn't just rubber stamp the work comes down to how you construct the context window and the system prompt for that subagent.
Okay.
You aren't just asking Claude to check its work. You are spinning up a completely isolated instance of the model.
Oh, so it's fresh.
Completely fresh.
Yeah.
This subagent does not see the agonizing, convoluted thought process the main agent used to arrive at the plan. It only sees the final proposed architecture and the original goal. Furthermore, the subagent is given a completely different system prompt, one that heavily weights skepticism, security, and scalability. It acts as an adversary, it looks at the proposed data flow and pushes back, saying, this state management approach won't scale, revise it.
So you are structurally enforcing a separation of concerns. The creator agent is optimized for generation, and the reviewer agent is optimized purely for critique, with a totally clean context window.
Exactly.
That makes a lot of sense. So if the planning phase stops the massive architectural disasters, how do we catch the death by 1,000 cuts? The spaghetti code, the performance hits, the visual misalignments. This leads us to the advanced guardrails.
This is where Costa moves beyond basic syntax checking and automates backpressure for highly subjective human values. The first, and what he actually considers the most effective mechanism, is the use of review agents.
Oh, I know.
These run on every iteration and parse the actual diffs the main agent produces.
How do they mechanically inject pushback, though? Are they just looking for missed semicolons?
No. The compiler catches semicolons. The review agents are evaluating heuristics like cyclomatic complexity, loose type definitions, and general readability.
Oh, wow.
Yeah. Mechanically, the system takes the newly generated code, passes it to the review agent, and asks, is this function too complex? Does it violate our specific brevity guidelines?
And if it does?
If the review agent flags a block of code, it intercepts the loop. It prevents the main agent from moving on, injecting a prompt that says, refactor lines 40 through 60 to reduce nesting before proceeding. It basically automates a senior developer's intuition.
That's incredible. Then he introduces pull request monitoring, which he calls the second most effective guardrail. This takes the backpressure out of the local loop and applies it to the actual repository.
Exactly. Because even with local subagents, code behaves differently when it interacts with the broader main branch.
Always does.
Costa built a skill that monitors a newly opened PR for a set amount of time. It acts as a webhook listening to GitHub events.
Okay, smart.
If the remote CI fails, or if there is a merge conflict, or even if another automated bot leaves a critical comment, this monitoring skill scrapes that data. It grabs the terminal output, wraps it in a prompt, and automatically kicks the PR back to the main agent to fix.
No expensive clipboard required.
Exactly.
You don't have to monitor your email for a failed GitHub action. Copy the log and paste it to Claude. The system intercepts the failure and routes it directly to the model.
Yep.
He also gave the AI the ability to do local manual testing. Using a tool called Obra Superpowers, he actually gave Claude access to a bash shell and a local browser.
This bridges the gap between isolated unit tests and real-world execution. The AI can literally execute a curl command against the local server it just spun up using Docker Compose.
It can read the JSON response?
Yes. If it expects a 200 OK and gets a 500 internal server error, the AI has to read the stack trace and write a patch itself. Costa notes this is slower because of the execution time, so he uses it sparingly. But it is a massive leap in autonomy.
Okay, here's where it gets really interesting, though. The visual design reviews.
Ah, yes.
When I read this section of Costa's post, I was incredibly skeptical. I mean, code is math, right? It's logic. A test either passes or fails. But visual design, aesthetics, Isn't that way too subjective for an AI to review accurately without just, hallucinating design feedback?
Your skepticism makes total sense, and Costa notes this is highly experimental, but the mechanics of how he executes this are just brilliant.
Okay, walk you through it.
He doesn't just pass a screenshot to a vision model and ask, hey, does this look good? That prompt is way too vague and basically guarantees hallucinations. Instead, he turns a subjective aesthetic judgment into a measurable mathematical boundary.
Walk me through the actual mechanics of that. How does the AI look at a web page and measure it?
He uses a tool called the Playwright MCP. Playwright is a testing framework that can spin up a headless browser.
But I've used Playwright.
So when the AI finishes a front-end component, Playwright physically renders the page and takes a screenshot. The system then compares that screenshot against strict design tokens from a Figma file or a linear ticket. But it doesn't evaluate the whole page at once. It uses strict bounding boxes.
So it breaks the layout down into atomic pieces.
Yes, exactly. It isolates the header, then the main content block, then the footer. It compares the rendered output against the design file heuristics.
Oh, wow.
It measures specific CSS values. Are the elements misaligned? Is the padding exactly 16 pixels as defined, or is it 12? Is the color contrast mathematically accessible? By breaking the visual review down into localized, specific structural diffs, he totally removes the vibes from the equation.
Right, it's not about vibes anymore.
No, the subagent isn't judging beauty, it is judging strict compliance to a design system. It pushes back by saying, the primary button hex code doesn't match the Figma token and the margin top is off by 4 pixels. Fix the CSS.
That completely flips the paradigm. It turns visual QA from a human staring at a monitor squinting at button alignments into an automated compile time error.
It really does.
So what does this all mean? We have covered a tremendous amount of system architecture today. How does a listener actually use this workflow tomorrow morning without spending a month building bespoke Python scripts?
Well, Costa actually packaged this exact workflow into an open source tool. You can open your terminal today and run npx at Lucas Costa Backpressured.
And what exactly does that execute?
It installs the required skills and scaffolding. Once it's running, you go into your Claude interface and type backpressured followed by your goal description.
Just like that?
Just like that. The agent takes over. It autonomously loops through the linting, the test generation, the review agents, and the PR monitoring we just discussed.
Okay, but how do you customize it? Because my team's coding standards are obviously going to be different from yours. Do I have to fork his entire repository to change the rules?
No, and this is the most elegant part of the implementation. You simply add a markdown file named backpressure.md to the root of your project repository.
Oh, really?
Yeah. You write your rules in plain English. The tool parses this file and injects it directly into the system instructions for the LLM. Because it's injected as high-priority constraints, the model prioritizes your specific definitions of readability, architecture, and testing standards during the iteration loop.
That is amazing. It takes esoteric systems engineering concepts, control theory, automated backpressure, sub-agent routing, and boils them down to a single terminal command and a plain English markdown file.
It's extremely accessible.
So what does this all mean? If we connect this to the bigger picture, Costa leaves us with a pretty profound operational maxim at the end of his post.
If we connect this to the bigger picture, he states, any system that relies on a human to catch the machine's mistakes will be limited by the human, not the machine. Throughout the entire history of computer science, our greatest leaps in productivity came when we built tools to take the manual verification away from humans. We built compilers so we didn't have to check memory allocation manually. We built CI pipelines so we didn't have to run test suites locally.
Right.
Now that we have code that writes itself, we have to build the next layer of abstraction. We have to automate the oversight.
We have to stop acting as the manual clipboard between the machine that writes the code and the machine that runs it.
Exactly.
We are moving from a paradigm of either letting the hyperactive intern burn down the staging server or staring over their shoulder at every single keystroke to building an automated, self-correcting factory. You give the factory a goal, and the system itself provides the necessary friction. The subagents, the linters, and the visual reviews push back on the AI relentlessly until the output quality is actually worth a human being's time to review.
It completely elevates the human's role in the development cycle. When you are no longer burdened by low-level syntax errors, missing test coverage, or padding misalignments, you reclaim your cognitive bandwidth. You finally have the time to focus on deep architectural decisions, user experience, and the actual business logic of what you are trying to build.
So, as you head into work this week, Take a hard look at your own workflow. Pay attention to the moments where you are acting as the bottleneck. Ask yourself, where am I serving as the default manual back pressure for a machine that is entirely capable of checking its own work?
This transition in how we build software raises an inevitable question, something for you to mull over as you begin deploying these autonomous workflows.
Let's hear it.
If AI agents are writing the bulk of the logic and a dedicated team of sub-agents are reviewing the architecture, checking the visual design, and monitoring the pull requests, what exactly is the human's job in 5 years? Do we eventually stop being creators altogether and simply become the assigners of goals?
The assigners of goals. From hand typing every single semicolon to holding an expensive clipboard to eventually just pointing at the horizon and letting a swarm of agents figure out how to navigate the terrain, it is a wildly fascinating time to be building technology. Thank you for joining us on this deep dive. Go try running NPX at Lucas Backpressured in your terminal. See if you can finally automate your own hyperactive intern. And above all, stay curious. We will catch you next time.